Welcome to the deep dive. Today we're going to try and get to the bottom of physics. The fundamental laws, and we're going to be using Physics for Dummies as our guide. And I have to admit, makes me feel a little bit better about all this crazy stuff.
Oh, it's a great place to start. And even if you already kind of know the basics, there's always, more to learn with physics. Always deeper layers.
Yeah. Okay. So the book starts out with measurement systems, which I guess makes sense, right? Like you can't really talk about physics without first figuring out how to measure things. But there seems to be like a bunch of different systems that physicists use. So like, what's the deal with that?
Well, consistency is key in physics.
Mm.
You know, whether you're talking about centimeters or meters, grams or kilograms. I mean, the units that you're using have a huge impact on how accurate your calculations are. I mean, imagine you're trying to build a bridge, but the blueprint has like mismatched measurements.
Oh yeah, that'd be a
It's a
disaster.
total disaster.
The book actually mentioned the student who like totally messed up this whole physics problem just because they forgot to convert the units. And it makes me wonder how often like stuff like that happens in real life, you know? In like real world situations.
It's probably way more common than you think. And that's
Mhm.
why physicists pay so much attention to significant digits, because those tell you how precise a measurement is. And like, if you claim more precision than you actually have, you can end up with misleading results,
Oh yeah, I see.
which could be dangerous sometimes. Like, imagine you're trying to calculate the trajectory of a spacecraft.
Oh gosh, yeah.
A tiny error in the precision could send it way off course.
That's true, yeah. So I guess like every little decimal point really does matter in physics.
It does. It really does.
Okay, so we've got the units down. So what's next?
Well, let's move on to one of the most, I guess, basic concepts in physics.
Yeah.
And that's motion. I mean, we experience it every single day, but understanding the laws that, govern it, it can be kind of tricky.
Yeah. Well, the book starts with speed, which seems pretty straightforward. Distance divided by time, like figuring out how long it would take to drive from New York to LA.
Right. But then things get a little bit more complicated when you start talking about acceleration.
Hmm.
It's not just how fast something is moving, but how quickly that speed is actually changing.
Yeah.
And that's where vectors come in. So like acceleration has both magnitude and direction. Think about a car chase. If the getaway car is speeding up, that's positive acceleration. But if they slam on the brakes, that's negative acceleration, also called deceleration.
Right.
So both of those, they affect the car's overall motion, and you need, different calculations for each one.
Oh, vectors. Those take me back to high school physics, like all those little arrows going every which way.
Yeah.
But I guess it makes sense that direction matters when you're talking about, how something's moving. So we've got speed, we've got acceleration. What other big concepts come into play when you combine those?
Well, you can't really talk about motion without talking about force. So force is what causes objects to move, to accelerate, or change direction. And our understanding of force, really, it comes down to Newton's laws of motion.
Ah, yes, Newton.
Yeah.
I feel like those laws are super important, but like if I'm being honest, I couldn't tell you what they actually are.
Oh, that's okay. We'll break them down. So
Okay.
the book actually focuses on Newton's second law,
Yeah.
which basically states that force equals mass times acceleration. So a larger force that you apply to an object, that will result in greater acceleration.
Right.
And a heavier object is going to need more force to get the same amount of acceleration. So think about like pushing a shopping cart versus pushing a car.
Right.
That car has way more mass. You're going to need a lot more force to get it moving.
Okay. Yeah, that makes sense. So what about inertia?
Yes,
I feel like I remember that word from somewhere. So does that have something to do with force too?
it totally does.
Yeah.
So inertia is an object's resistance to changes in motion.
Hmm.
The more massive something is, the more inertia it has. So that car, not only does it need more force to get moving, but it also wants to stay at rest or in motion way more than that shopping cart. It's stubborn.
I'm starting to see how all these concepts kind of like work together.
Yeah.
Force, mass, acceleration, inertia. It's like this little dance between these different factors
Absolutely.
that determines how things move. So what happens when a force is applied over a distance? Is that where work and energy come in?
You got it. So in physics, work isn't just about effort. It's specifically defined as force multiplied by distance. Picture this. You are pushing a heavy gold ingot across the floor. The more force you apply over that distance, the more work you've done.
So if I just stood there holding the gold ingot, like I wouldn't actually be doing any work, even though it felt really heavy.
Nope. No distance, no work.
Interesting.
Yeah, and
Yeah.
energy is like the ability to do work.
Mm-hmm.
And we have kinetic energy, the energy of motion. Think of like a rolling bowling ball.
Right.
And then there's potential energy, which is stored energy, because of an object's position. So like a roller coaster at the top of a hill,
Right, right.
just like full of potential energy, ready to be unleashed as kinetic energy when it goes down the track.
Oh, I love roller coasters. I never really thought about the physics behind them, but that makes sense. The higher the roller coaster climbs, the more potential energy it gets. And then the faster and wilder the ride is as all that energy turns into motion.
Exactly. And one of the most fundamental principles in physics is called the conservation of mechanical energy. And it states that in a closed system, the total amount of mechanical energy, it always stays the same. So even though a roller coaster's energy is like transforming between potential and kinetic, the overall amount of energy is constant.
Wait, so does that mean we could actually calculate things like how fast a roller coaster is going or how high a ball will bounce just by understanding this energy conversion?
Exactly. It's a really powerful tool for solving all sorts of physics problems. And it brings us to, one of the most mind-bending aspects of physics, Einstein's theory of relativity.
Here's where things get really interesting. The book says that special relativity, it tells us that time and length aren't absolute. Like they can actually change near the speed of light, which just sounds like it's out of a sci-fi movie.
It really challenges how we think about reality every day. I mean, imagine this. If you were traveling at close to the speed of light, time would actually slow down for you compared to someone standing still.
Wow, that's incredible. It's hard to wrap your head around that. And then there's that famous equation E mcxo. What does that actually mean?
It is one of the most profound equations in all of physics.
Hmm.
Basically, what it's telling us is that mass and energy, they could be swapped.
Mm-hmm.
So a tiny amount of mass can be turned into a massive amount of energy, which is why nuclear reactions are so powerful. It's actually how the sun produces energy. And it has huge implications for everything from nuclear weapons to the future of energy.
So even a little tiny bit of matter can unleash all this energy. That's kind of scary but also fascinating, and it's all because mass and energy are essentially the same thing.
Exactly. And this leads to some other really interesting concepts in physics, like the uncertainty principle, which says that it's impossible to know both an object's momentum and position perfectly at the same time. The more you know about one, the less you know about the other.
That's so weird. So it's like you're trying to grab a shadow, the harder you squeeze, the more it slips away. So the more we find out about physics, the more mysterious it gets.
Yeah, that's the cool part about it. There's always something new to find out, and how we understand the universe is always changing, always evolving. And here's something to think about. So the book ends by saying that physicists haven't found any truly absolute physical measures.
Wait, so are you saying our observations could actually be shaping reality? Does that mean there's no real objective truth when it comes to physics?
Yeah, it's possible.
Hmm.
And it raises some pretty deep questions about what reality actually is. Maybe how we see things influences what we measure. And just by observing something, we're changing it.
Whoa, that's a lot to take in.
Yeah.
We went from basic measurement systems to questioning the very fabric of reality.
Yeah.
I feel kind of overwhelmed, but also super intrigued.
That's the thrill of physics.
Yeah.
And we've really only just started. There's a whole universe of cool concepts just waiting to be explored.
Yeah, I'm ready for more. So what other mind-blowing physics stuff will we be talking about in our next deep dive?
We'll be looking at the world of forces and inclined planes, and we'll even throw in some friction for good measure. Be ready to see how all those things work together to create motion.
Okay, I think I'm ready to tackle those inclined planes, the ones you were talking about.
Yeah.
Sounds like we're going to take physics to a whole new level, literally.
Well, inclined planes, they might seem kind of simple
Yeah,
at first,
yeah.
but they're a really cool way to study how forces work together to make motion.
So we're not just talking about ramps for loading trucks anymore.
Well, ramps are like the classic example.
Yeah.
But the same, ideas apply to any surface that's at an angle, to the horizontal.
Mm-hmm.
Think about a slide at a playground,
Right.
a snowy hillside, or even like a winding mountain road.
Okay.
I mean, those all use inclined planes.
Okay, yeah, yeah. I'm starting to see how inclined planes are kind of all over the place. But how do forces work differently on an incline, versus a flat surface?
Well, gravity's a big factor here.
Yeah.
On a flat surface, gravity just pulls straight down, right?
Right.
But on an incline, Gravity's force is actually split into two parts. So
Oh,
one part is pulling the object down the incline,
okay.
and the other is pressing it against the surface.
Oh, so it's like gravity's working in two directions at the same time. Does that mean, like, an object's weight actually changes on an incline?
No, its weight's the same,
Okay.
but the force pulling it down, that changes. So the steeper the incline is, the stronger that force gets. Think about trying to push like a heavy cart up a steep hill
Right.
compared to like a gentle slope.
Yeah.
The steeper it is, the more effort it takes to like overcome that force pulling it down.
Right, right, yeah. And you mentioned friction earlier.
Yeah.
So how does that fit in on an incline?
Friction is always there. It's like always, resisting motion. On an incline, it's like this constant tug of war
Uh-huh.
between the force pulling the object down and friction trying to hold it back. If that downward force is strong enough to beat friction, then the object will start to slide.
Okay, I'm picturing a refrigerator balanced on a ramp, like super precariously.
Hmm.
So is there a way to calculate how much force it would take to like get that fridge moving or to keep it from sliding in the first place?
Definitely. We can totally calculate the forces involved using something called static and kinetic friction.
Hmm.
So static friction, that's the force you need to overcome to get something moving from rest,
Okay.
like pushing that fridge.
Yeah.
And kinetic friction, that acts on something once it's already moving,
Okay.
trying to slow it down.
So static friction is like the initial push to get things going, and then kinetic is like trying to put on the brakes.
Yeah, exactly.
But how do we actually measure those forces?
We use something called the coefficient of friction, which basically, it depends on what kind of surfaces are involved. So rough surfaces like sandpaper,
Yeah.
they have a higher coefficient of friction than smooth surfaces like ice.
Okay.
And then there's the normal force, which is the force that the surface is pushing back on the object.
So the type of surface and like how much the object is pressing on it, that all affects friction.
Yeah.
So does that mean like we can actually calculate how fast that fridge would slide down the ramp?
For sure.
Yeah.
We consider the force of gravity pulling it down,
Right.
the force of friction working against it, and how heavy the fridge is, and we can figure out how fast it'll accelerate. It's all about understanding how these different forces all work together.
Okay, my brain is starting to feel a little bit fried with all these forces and friction and stuff. Can we move on to something a little bit less slippery?
Yeah, let's how about something that goes round and round?
Okay.
My book has a whole chapter about circular motion and orbits.
Sounds like we're about to hop on the physics merry-go-round. What are like the main ideas we need to know about circular motion?
One of the most important is centripetal acceleration.
Okay.
That's the acceleration that makes an object move in a circle, even if it's moving at the same speed.
Wait, so something can be accelerating even if it's not speeding up or slowing down? How does that work?
Well, remember, acceleration is any change in velocity,
Uh-huh.
and velocity includes both speed and direction.
Right.
So in circular motion, the object's direction is always changing,
Okay.
which means it's always accelerating. Think about like a ball being swung around on a string.
Right.
The string keeps the ball going in a circle, and that inward force is what's creating this centripetal acceleration.
So even though the ball might be moving at a steady speed, the fact that its direction is always changing, it's still accelerating, and that string is providing the force to make that happen.
Exactly. And that force, towards the center of the circle, that's what we call centripetal force.
Okay.
It's not like some, brand new force. It's just the force needed to keep the object moving in that circle. Could be tension in a string, friction between tires in the road, even gravity, like with a satellite orbiting the Earth.
Oh, okay. So centripetal force is like the glue that holds everything together in circular motion. So is there a way to like calculate how much force is needed?
Of course. We have an equation for that. It uses the object's mass,
Yeah.
how fast it's moving, and the radius of the circle. So a heavier object moving faster in a smaller circle, it'll need more centripetal force. Think of like a figure skater spinning.
Right.
The faster they spin, the tighter they pull their arms in, the more force they need to keep spinning.
Okay, now I'm picturing those Olympic figure skaters.
Huh.
Like all those forces at play. Okay, so let's talk about orbits. How does circular motion apply to like a satellite going around the Earth?
Well, that's where gravity really comes in. When something is in orbit around something else, gravity provides that centripetal force to keep it moving in that circle. So it's like the Earth is constantly pulling the moon towards it so it doesn't just fly off into space.
So gravity is what's keeping the moon from like going rogue and just wandering off on its own. But if gravity's pulling it towards Earth, why doesn't it just like crash into us?
It's all about the balance between gravity and speed. So the moon is always falling towards the Earth, but it's also moving forward at just the right speed to keep missing us. Imagine throwing a ball horizontally.
Yeah.
The harder you throw it, the farther it travels before it hits the ground.
Right.
Well, the moon is basically in constant free fall, but it's moving forward enough to stay in a stable orbit.
So it's like the moon is on a roller coaster that never ends, just constantly falling but never actually hitting the bottom.
Exactly.
Wow. And is it true that like satellites can only have one speed when they're in orbit at a certain distance from Earth?
That's right. The force of gravity at that distance, it determines the speed the satellite needs to stay in orbit.
Okay.
So if it speeds up, it'll move farther away, and if it slows down, it'll get closer to Earth. It's a delicate balance.
Yeah.
It takes some really precise calculations to make sure the satellite stays on track.
Okay, this is all super interesting, but my head is spinning a little bit from all this talk of forces and acceleration and orbits.
I I, I get it. It's a lot to wrap your head around, but we've covered a lot of complex stuff,
We have,
and
yeah.
we're making good progress.
Yeah. So, I'm ready to take a break from all this like spinning and sliding. What's next on our physics adventure?
Well, let's dive into the world of work and energy, and we'll see how those ideas are like really important for understanding how things move and change in the physical world.
Okay, so let's get into this whole work and energy thing. I feel like those are words we use all the time, but I have a feeling in physics they have like a deeper meaning.
Yeah, you're totally right. In physics, work and energy have very, very specific definitions, and they're super important for understanding how things move and interact in the physical world.
So let's start with work. So the book says work is defined as force times distance. So does that mean every time I lift a weight at the gym, I'm doing work?
Yep, yep, exactly. You're applying force to lift the weight, and you're moving at a certain distance, so you're totally doing work. And the heavier the weight or the higher you lift it, the more work you're doing.
Okay, that makes sense. So then what about energy? How does that fit in? Is it like the fuel that lets us do work?
Yeah, you can think of it that way. Energy is the ability to do work. And it exists in lots of different forms, but two of I guess, the most basic types are kinetic energy and potential energy.
Right, right. Kinetic energy, energy of motion, like a speeding car or a rolling ball. And potential energy is stored energy, based on an object's position or state, like a roller coaster at the top of a hill or a stretched rubber band.
You got it.
Uh,
And the really cool thing is that those two types of energy, they can be converted into each other.
yeah.
Like think about that roller coaster again.
Yeah.
As it climbs the hill, it's gaining potential energy. And then as it goes down the track, all that potential energy changes into kinetic energy.
So it's like a constant like back and forth between potential and kinetic. But if energy is always changing forms, does the total amount of energy ever change?
That's where the principle of conservation of mechanical energy comes in. It says that in a closed system, the total amount of mechanical energy always stays the same. So even though the roller coaster's energy is, changing between potential and kinetic, the total amount in the system stays constant.
Okay. So I'm starting to see how this principle could be really, really helpful for understanding all kinds of motion. Could we use it to like figure out how fast a skateboarder will be going at the bottom of a ramp or how high a ball will bounce after being dropped?
Absolutely. We can totally use the principle of conservation of energy to calculate those things, and it's a super important tool for solving all sorts of physics problems.
So we've got work, we've got kinetic and potential energy, and this principle of conservation. Anything else we need to know about energy?
Well, there are different types of forces that affect how energy is transferred or transformed. You've got conservative forces like gravity that don't depend on the path taken. And then there's non-conservative forces like friction that do depend on the path.
Okay, can you give me an example of how that works?
So imagine like pushing a box across a rough floor. The work done by friction depends on how you push it. If you push it in a straight line, the work done by friction will be less than if you push it in like a zigzag.
So friction is basically like stealing some of the energy that we're putting into pushing the box, and the longer the path, the more energy it takes.
Exactly. Friction takes some of that energy and turns it into heat, which is why you might feel like the box or the floor getting warmer.
Wow, this whole deep dive has been pretty incredible. We've gone from like measuring stuff and understanding motion to exploring energy and relativity, I feel like I've got this whole new understanding of how the world works.
That's awesome. I'm glad to hear that. Physics can be tough, but it's so rewarding to unlock these secrets of the universe. And remember, even though we've covered a lot, this is really just the start. There's a ton more to explore in physics.
I definitely want to learn more. Thanks for taking me through this deep dive. It's been awesome.
Of course, it's been fun. And remember, physics isn't all, equations and theories. It's all around us. It affects everything we do. So be curious, keep asking questions, and you never know what amazing discoveries you might make.